So now that we've got it all kind of mapped out on the periodic table, the different orbitals and energy levels and spins, we're going to keep going on with the rules for writing electron configuration. So this would be the second rule, and it's called the Pauli exclusion principle. And this says that no two set of electrons in an atom can have the same set of 4 quantum numbers. And then every orbital is capable of holding 2 electrons. So a lot of times you'll see orbitals drawn as squares, or sometimes the circles will represent orbitals. And then, so those represent orbitals. And then the arrows represent the electrons. And remember, the up represents one spin and the down represents another spin. The third rule is Hund's rule, and this says orbitals of equal energy are each occupied by 1 electron before any orbital is filled with a second electron. And it also says all unpaired electrons will have the same spin. So for example, hydrogen has 1 electron, so we have it in the 1s orbital, and we represent it with 1 arrow. Helium has 2 electrons, so we have to put it in the 1s as well. And notice now that it has the down arrow representing that second electron for helium. Lithium has 3 electrons, and so we have to fill this 1s first, and then according to the periodic table, the next one to fill would be the 2s. And since we only need 3 electrons, we just put the 1 arrow in there. And so notice that we have opposite spins when we have them doubled up. So let's practice doing all of this. So it says draw the orbital filling diagram for carbon. So the first step is to locate carbon on the periodic table. So things to note is its energy level. And for carbon, it is in the second energy level because it is in the second row. And then what orbital it has. So remember, this is the S block and this is the P block. So our orbital is the P. And so we know our energy or electron configuration has to end in sp, and then notice this is the 1, 2 second element in that P block. So it will have 2 electrons there. So to do our orbital filling diagram, we have to work our way all the way from hydrogen down to carbon. And so that means we have our drawn orbital, and this one represents our 1s level, which would be this row right here. So hydrogen and helium. And then we move down to the second row, and our next block that we come across is our 2s. And then next we enter into this P block, and we call it 2p. Remember, P has 3 orbitals. We call it 2p because it's in the second energy level. So now we need to fill in the electrons that would go in to those sublevels. So we have to fill the lowest one first, and it gets 2 electrons. And so remember, we need a total of 6 electrons here. And then we fill in the 2s, and then we can move into the 2p. And so since right now we have a total of 4 electrons, we only need 2 more. And so they have to go in as unpaired. And that's to fulfill Hund's rule there. And so this is carbon's electron orbital filling diagram. It shows you the order in which the electrons fill. From this, you can write the electron configuration for carbon. And this is where you take your orbitals and energy levels, and you indicate then how many electrons are in that orbital. So we have 2 in there. Then our next one is the 2s. And again, there's 2 electrons that fill that. And then lastly, we have our 2p, and we have 2 electrons there. So the electron configuration for carbon is 1s2, 2s2, and 2p2. So now our next example here is for magnesium. So I'm just going to erase what we have all written here for our carbon. So then we can look for magnesium on the periodic table. And here we know that we need 12 electrons. And so starting with the top of the periodic table, we have to deal with this first row. And in there we only have the 1s. Remember, we start at the bottom, 1s. Then our next chunk comes from the 2s. There's only 1 possible orbital for that because it's in the s block. Then we're still in the second energy level, but we've now entered into the p block. So we call that 2p. And then we have to go down into the third energy level, and that's in the s block. So we'll have 3s. And since we've reached magnesium, we don't need to go into that 3p area. And so now we can fill in our electrons. And so everything needs to be filled from the bottom to top. So 1s gets filled, the 2s gets filled. And then remember the 2p, you have to do all of the ups. And then you can go back to that first orbital and fill in all of the downs. And here we're at 2, 4, 6, 8, 10 electrons. And so then we can fill in electron number 11 and 12 to get to magnesium, because magnesium has 12 electrons. So then to write the electron configuration, you simply write what you have drawn out here. So we've got 1s, and that has the 2 electrons in it. Then we have 2s, also having 2 electrons. Then we go to 2p, and here we have 6 electrons, 2 in each orbital. And then lastly, we have the 3s, and that also has 2 electrons in it. And so that would be the electron configuration for magnesium. So when we look at this, we can also look at valence electrons. These are the electrons that occupy the highest principal energy level. And so if we look at this particular orbital configuration, it's asking how many valence electrons are in the orbital configuration for the element above. So here you have to find your highest occupied principal energy level. So that would be the 2s out front. And so to figure out how many valence electrons you have, you look at every orbital that has a 2 out front, and see, all right, we have 2 there, plus the 4 electrons here. So we have a total of 6 valence electrons. So we can figure that out from either the orbital filling or the electron configuration. And the other thing we can figure out is what element it is. And so one way to do this is to look at your periodic table and say, all right, here we have 1s and there's 2 electrons. So here's 1s1, 1s2. Then we move to the 2s, and so we have 2s1, 2s2 for the 2 electrons there. Now we're into this 2p block, and we know there's 1, 2, 3, 4 electrons. So here in the 2p, and you count 1, 2, 3, 4 electrons. So this element happens to be oxygen. Which indeed has 6 valence electrons. The last thing to talk about is noble gas notation. So If you have to write out an element, a big element like gold or silver or I don't know, one that has lots of electrons, your electron configuration would be huge. And so we use noble gas notation as a kind of shorthand. And so this is a way to use the elemental symbol for the last noble gas prior to that atom is written first, followed by the configuration of the remaining electrons. So I think maybe the best way is just to practice this. And so here are your electron configurations for a bunch of elements in that, I think is it the second or third energy level? Third energy level. And so if we look for calcium, this is here, and you count backwards, so 20, 19, 18, we get to argon. So argon is the noble gas prior to the atom. So in brackets, we write argon symbol. And then from there, we can write our electron configuration for calcium. So after argon, you enter into that fourth energy level. And calcium is in that S. And it is the 1, 2, second atom or second electron to fill on that 4s orbital. So that would be the noble gas configuration for calcium. So let's try another practice one here. So let's try the noble gas configuration for phosphorus. So again, if you count backwards, so 14, 13, 12, 11, 10 that would be the closest noble gas. So neon goes in the brackets. And then from neon, you count down just like you normally would. And here we enter the third energy level in the S block. And you need to fill both of those electrons, so it's 3s2. And we're still not to phosphorus, so we scoot across. Still in that third energy level, and we're now in the P block. But this time it is the 1, 2, 3, third electron. So that would be your way to write the noble gas configuration for phosphorus. And so I think that's all for electron configuration and orbital filling.